Hello. In the previous video, we learned that if we split a very large nucleus, such as the uranium-235, we can obtain two smaller nuclei with higher binding energy per nucleon. This indicates that energy is released during the fission of uranium-235. Let's try it out with this applet here. This gun here is going to emit neutrons. Every time I press the button, it will emit a neutron. Now let's bring in some uranium nuclei. So all these are uranium nuclei. So when I press the button and when a neutron hits the uranium nucleus, it's going to undergo fission and splits into two. Let's go. Why nothing happened? Why nothing happened? What? Who put the wrong nuclei here? These are uranium-238, not uranium-235. Now there are a few uranium isotopes and only one of them can undergo fission. The most common isotope is the uranium-238. In fact, uranium-238 makes up more than 99% of naturally found uranium. The uranium isotope that is capable of fission is uranium-235. And in any naturally found sample, less than 1% of them are uranium-235. So when you hear that Iran is suspected of enriching uranium, what we mean is they're trying to separate uranium-235 from uranium-238 so that they can build a nuclear bomb or something. Okay, let's swap out the uranium-238 and bring in the uranium-235. Okay, I'm going to press the button once. Kaboom, 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 kaboom. Oi, what's happening? I pressed this button only once, that means I released only one neutron, and yet all of them are gone. How come? Okay, let's look at the fission process in more detail. The fission of uranium-235 actually requires a trigger, and the trigger is provided by a thermal neutron. This neutron is not a very energetic neutron. In fact, it doesn't work if this neutron is traveling too fast. Now, after the uranium-235 gobbles up this neutron, it becomes unstable, and then it will split itself into two. Does it always split itself into strontium and xenon? Actually, no. It can split itself into any two nuclei. Listed here are only 5 of hundreds of possibilities, as long as the number of protons in the two fission nuclei still add up to 92. And of course, the total number of neutrons must remain the same, which means the total number of nucleons must also remain the same after the fission, which means like 235 plus 1 here is equals to 95 plus 139 plus 2. 2 neutrons here. So notice that we fed 1 neutron to this uranium, but the outcome of the fission is we actually have more neutrons than before. We end up with 2 neutrons, and sometimes we even end up with 3 neutrons after the fission. So let's visualize what happens during the fission, So this is the uranium-235. It starts off at rest, very little Ke. We feed this neutron to it. After the uranium-235 gobbles up the neutron, it becomes unstable. See, it's shivering here. So what does it do? It splits itself into two. What's shown here is krypton-91 and barium-142 with some bonus neutrons. 3 of them shown here. We said that a lot of energy is released during the fission, right? So where does the energy go to? It goes into the Ke of these fission products. So after the fission, you see all these fission products traveling at very high speed. So we start out with 1 neutron, but after the first fission, we can end up with up to 3 neutrons, which can go on to trigger 3 more fission. And now we end up with 9 neutrons. So you can see how we end up with a chain reaction, because we go 1, 3, 9, 27, 81, 243, 729. I have to stop here. But you get the idea, So if you have a sample of highly enriched uranium, full of uranium-235, then starting with 1 fission, you can start off a chain reaction that ends up as a uranium bomb. Uranium is also used in our nuclear plants to produce electricity, right? So what happens in our nuclear plants is we use boron rods. Boron is a material that's able to absorb neutrons. So we use the boron rods to control the number of neutrons in the nuclear power so that we have a steady release of energy instead of a nuclear blast. Now let's try to do an energy calculation. So how much energy do you think is released during the fission of uranium-235 into krypton and barium? For that, we need to know the binding energy per nucleon of all these nuclei here. So for the uranium-235, it's 7.60 mega electron volts per nucleon. For the neutron, it's 0. Why is it 0? Because the neutron is already the basic nucleon. We don't split it anymore, right? So the neutron has no mass defect and therefore no binding energy. Let's continue. For the krypton, it's 8.57. For barium, it is 8.31. And of course, these 3 neutrons also have no binding energy. So these are the binding energies per nucleon. So how do we get the total binding energy? For the uranium-235, we are going to take 235 because that's the number of nucleons in uranium-235. So we take 235 times 7.80 mega electron volts per nucleon. We end up with 1786 mega electron volts. So that's the binding energy for the uranium-235. We do the same thing to krypton and barium. So we take 91 times 8.57 plus 142 times 8.31. And then we sum up the two binding energies, we get 1960 mega electron volts. So do you notice that after the fission, the total binding energy has increased by about 170 mega electron volts. So that's the amount of energy released. That means if you add up the Ke of the krypton and barium, it's going to be roughly 170 mega electron volts. Now, is this a very large amount of energy? By itself, it's not very large, yeah? To convert mega electron volts to joules, remember you've got to multiply the electronic charge, 1.60 times 10 to the power of negative 19, right? So by itself, this is only about 10 to the power of negative 13 joules of energy. But this is the energy released by the fission of one single uranium-235 nucleus. So if you're talking about 1 mole of uranium-235, which is just about 235 grams of uranium, we're talking about something of the order of 10 trillion joules of energy. Now, it's a pity that nuclear fission was first used as a weapon of mass destruction. And because of this, many societies have this phobia of nuclear energy, which is rather frustrating because nuclear power can really help us reduce our reliance on fossil fuels. Climate change is literally destroying the lives of a lot of people in many countries today. I think as societies, we really have to stop being so childish and to consider seriously how to use nuclear power to save ourselves. Alright, that's all. Ta-ta!